This talk will discuss the design and construction of the first solar farm in Europe to be developed on peat and highlight the innovative approaches adopted to address the engineering and logistical challenges of building a solar farm on peat. Our speakers this evening from the ESB and Board Móna JV are Conor Sheridan, Chartered Engineer, who is a Project Director with ESB Asset Development, Móna Nocton, who is the Construction Project Director for the Timahoe North Solar Farm and who has over 19 years experience in the civil engineering industry. Shane Scally, Chartered Engineer, who is the Construction Project Manager for the Timahoe North Solar Farm and who has over 16 years experience in the civil engineering industry. I will now hand over to Conor Sheridan to start the presentation.
Thanks, Peter. Good evening, ladies and gentlemen. I'm delighted to be able to present with two of my joint venture colleagues from Board Móna on the Timahoe North Solar Farm project this evening. And hopefully we'll be able to give you some insights into the design and construction of the project. So I'll just go through the agenda to start with. So I'm conscious that there are a number of different committees co-hosting the event tonight. So some people may not be familiar with solar in Ireland at utility scale. So I'll just give a brief intro to the status play on solar in Ireland. Then I'll kick into the project itself. I'll give an intro to the project. I'll talk around the contracting strategy, and I'll also talk around solar design and pile design on the project. Then I'll hand over to my colleague Móna Nocton, who's going to talk around some of the planning and environmental elements of the project. He'll touch on program, and then he'll talk around the construction of the project. He'll then hand over to Shane Scally, who'll touch on the EPC commissioning of the EPC contract, and then we'll finish on some of the community and environmental benefits of the project. So to start with solar in Ireland, so I suppose the main policy driver in terms of renewable development is the Climate Action Plan. So that aims to have 50% reduction in greenhouse gas emissions by 2030 on 2018 levels and to be net zero by 2050. So I suppose the major part of the plan is around decarbonisation of the electricity system. And there's a target for 80% of the electricity demand to be from renewables by 2030. And then each, I suppose, renewable discipline has their own target. So on the solar side, it's 8 gigawatts of solar, 5 of which will be from utility scale. And then onshore wind is 9 gigawatts and offshore wind is 5 gigawatts. So solar will play a big part in the targets up to 2030 and beyond to net zero in 2050. So just give you an overview of utility scale solar in Ireland to date. So there's around 600 megawatts on the system currently. So the first project was energized in 2022. So there's been steady progress over the last 2 years, and that will increase year on year up until 2030. Just to give you an overview of how it compares to onshore wind, say. So in terms of a capacity factor, so capacity factor is basically the percentage time a plant operates over the course of a year. So on solar, capacity factors in Ireland are around 10 to 12%. That compares to onshore wind, which is around, depending on the projects, around 25 to 35%. So, it's not as productive as onshore wind, but you'll definitely need a combination of both combined with storage and some sort of dispatchable generation to transition to that net zero by 2050. So it will be an important technology to get there. And then I suppose all these targets, they have to, to develop them out and to build the renewable capacity. The projects need to be commercially viable. So in solar at the minute, there's two main route to markets. The first is RES, so that's Renewable Energy Support Scheme, and that's a government-backed scheme. So that will guarantee the price per megawatt hour over a 15-year period for a project. So it's run on a competitive auction basis. So developers with eligible projects would enter the project into the auction and compete for a contract for up to 15 years. And then the second one is the corporate power purchase agreements, or CPPAs. So again, that's for large energy users, like major tech companies who have data centers, who would procure renewable energy directly from a developer for a period of, say, 5 or 10 years. So hopefully that sort of gives you an overview of the policy in terms of renewable development at the minute, sort of gives you an overview of the state of play to date in terms of the megawatts on the system, and then the route to market for developers to develop the projects. So now I'm going to just give you an intro to the Timahoe project. So it's a 70 megawatt solar farm. It's located in County Kildare, just south of Enfield. It's a joint venture between ESB and Bord na Móna, and it's part of a wider co-development agreement between both parties to develop up to 500 megawatts of solar on former Bord na Móna lands in the Midlands. It's a RES 2 contract, so I touched on what RES was in the last slide. So it secured a contract in June of 2022, and the target is for the project to be fully operational by the end of this year. So now I'm just going to turn on my pointer and I'll give you a bit of an overview of the site itself. So the site itself, you can see this an aerial photograph of the project before construction started, and you can see an aerial photograph here with the planning layout. So it's a 2,000 acre site itself, the Timahoe North bog. So you can see outlined in green here. When the project is complete, the footprint of solar will be approximately 430 acres in 2 distinct areas, so 2 solar arrays north and south. You can see the area in the center here was zoned out during planning design. It's a lower lying area. You can see there's some flooding in the area in the aerial photograph. So when the project is complete, it'll have enough energy to power 25,000 homes. There's a new 110 kV substation constructed on the site to connect the project back into the national grid. So you can see this purple line that runs to the site of the site. So that's the 110 kV Derry to Minute line. So the project connects directly back into that overhead line. Just to give you some construction stats then, or stats of the overall site itself. So there's 14 kilometers of access track installed as part of the project. There's a 6.5 kilometer amenity walkway, which will be open to the public once the project is operational. And then on the solar install itself, so there's 62,500 piles installed to support the solar structure above and ultimately support the solar panels. And on the solar panel side, then there's 165,300 solar panels on site on the project. Okay, now I'm going to go into the contracting strategy. So it was a multi-contract strategy. So there was an enabling works package complete by Wills. So that really, you can see in this bottom photograph, that really was to construct the main access track into the site, construct the substation platform and a construction compound, and also to do some site clearance on the site. And then there was an electrical balance of plant, or EBOP contract. So that was carried out by HNMV. And that was to construct the new 110 kV AIS substation and the associated grid connection. So you can see in this top photo, that's an image from during the construction phase. And then the EPC contract, so that was for the design, build, and operate of the plant for the first 2 years. And that's been carried out by Voltalia, who are a French EPC contractor. Just a note on the owner's engineer then, so Jennings O'Donovan is the owner's engineer at the minute. So they brought the project really from the auction stage right up to now. ESB Engineering and Major Projects were the owner's engineer prior to the auction phase. So just touch on some key challenges pre-construction. This was the EPC supply chain. So this was common across the whole solar market for the first RES project, so RES 1 and RES 2. I suppose solar was a new industry in Ireland a lot of the EPC contractors are European based, and they hadn't mobilized Ireland and didn't know whether Ireland was a key market for them. So the EPC supply chain was definitely constrained, and it was a challenge to get contractors on board for the early res projects. Obviously, it's been the first solar project on peat in Europe, definitely, and if not in the world. So obviously there was no template of how to build a solar farm on peat. So we were really starting from scratch, and yeah, that definitely threw up a number of various challenges. And yeah, just to note on commodity price fluctuations. So I suppose people are well aware that since the war in Ukraine started in 2022, right before the Res 2 auction, there has been a lot of volatility in terms of commodity pricing and material pricing, and also just impacts on long lead items such as transformers and lead times for delivery of key pieces of equipment. So that was another big challenge on the project. Okay, so now I'm going to go into the sort of solar design and touch on some elements of that. So there was an early works agreement signed between the EPC contractor and the JV prior to the main EPC contract being signed, and that was really to progress through a phase of design optimization to come up with the most optimum design for the project. So a key part of that was carrying out an LCOE analysis. So LCOE analysis is common across the board on solar projects, but due to, I suppose, the ground conditions on this site, it really was a key focus to get the optimum design. So really, it's levelized cost of energy. It's a financial metric used in the energy sector to compare different designs or different technologies, and it looks at the capex and opex over the operational life of a project, and also the corresponding energy yield over the life of a project, and that gives you really an average cost of a unit of electricity produced by a plant over its lifetime. So it gives you euro per megawatt hour value. So you can compare, a particular design which has a euro per megawatt hour value against, a euro per megawatt hour value of a different design, and that allows you to come up with the optimum design, or the LCOE design for the project. So there was probably two phases in that. First was on the solar side, and then secondly on the civil. So on the solar side, you're looking at trying to have the most optimum yield for the project with the minimum capex. So some of the things that we looked at was around just the module type. We looked at the module orientation. So the final design on this project is 2P or 2 in portrait. We also looked at some scenarios with the modules in a landscape orientation. We looked at row spacing. So the big thing on row spacing is really that you're not having major shading on the panels from the panels in front, or the tables in front. So we would have looked at that. Obviously, the more shading you have, the more impact on your overall yield. We would have looked at tilt angle. So the final tilt angle on this project is 25 degrees, but we would have looked at various tilt angles. We would have looked at DC-AC ratio. So this was a major component of the LCOE analysis to try and get the optimum DC-AC ratio. So in solar, the energy is produced as direct current, but it needs to be converted back to AC or alternating current to be exported out onto the grid. So really on a solar project, you're constrained by your grid connection, or the megawatts that you have at your grid connection. But it is typical to over install at the DC side, so putting on more modules or more megawatts of modules than you have a grid connection for. And really the purpose of that is in the summer, is to optimize the yield from a project. So really, if you had a 1:1 DC-AC ratio, you would only have a limited period in any given day that you would be exporting at max capacity. But if you can install more DC capacity, that essentially flattens the curve, and you get more production in the important summer months. So really getting the optimum DC AC capacity for the project was a key metric in the whole LCOE design that we done. And then just on the civil side, so I suppose on the civil side it was all around the piles, and coming up with a commercially viable pile solution was a major impact in the overall success of the project, and I'll touch on that in the next number of slides. We did on the civil side. We did also look at access tracks and hard stand designs. I suppose all the access tracks were floating. The loadings were not as heavily loaded as you would see on a typical wind farm. So we were looking at the heaviest loadings, and I know Marcin is going to cover some of the construction elements on the access tracks in the slides. Later on, there was some additional shear vane tests done along the route of the access tracks to try and optimize the design there as well. And then, so that was sort of the civil side. And then just so you can see here, so this is the final layout of the two arrays, north and south. So it was 108 megawatt peak design. We've got string inverters. So essentially when the power is created at the module, it goes back to a string inverter. It's converted from DC back to AC, and then it goes from the AC back to transformer centers. So there was 12 transformer centers on site, and the voltage at the transformer centers is stepped up from 800 volts up to 33 kV, and from the transformer center, which you can see here in the green container, it goes back via an underground cable back to the substation, and from the substation at the grid transformer, it's stepped up again to 110 kV, and then out onto the grid or exported to the grid from there. Okay, so that hopefully gives you some overview on the solar design. So I'll go into the pile design now. And probably I'll just state that there is probably enough technical information to cover a full lecture on the pile testing and installation, but maybe somebody more qualified than myself can come back and give that presentation at a later date. But hopefully I'll give a flavour of what was done and the final pile solution. So really the pile design started back in 2017 with the site investigation. So to give you an overview of the geotechnical parameters on site, so you've got peat and then glacial till, and then down to bedrock. So the peat on site is an average of around 2.5 meters. So you can see the contours here that maps it out. But you have, particularly on the southern array, you have deeper pockets of peat. You can see 4.5 meters here. There's also a number of localized bands of silt, which are prevalent across the site. So particularly around the substation area, there was a band of silt there. And then you've also got a band of gravel, and the localized pockets of gravel that cause some issues around the pile design and the pile testing, and I'll touch on that in the next slide. So that predominantly, again, that's located around the substation on the southern array. So then after the site investigation, there was an initial constructability trial done in 2019. So really that was the first attempt at looking at, a viable pile solution. And there was 3 different piles looked at in that trial. So there was a bottom driven steel tubular pile, which you can see here. There was also a helical screw type pile. And then there was a Sigma pile. After the testing and from a technical and commercial perspective, the Sigma pile was the favored pile, and that was the pile that was brought forward to I suppose the next phase and the tendering phase for the project. Okay, and then after that, so early last year, there was a further pull-out test campaign done by Wills and their designer GDG So this was main contract signing on the EPC contract. So there was 128 Sigma piles installed, 4 different section sizes from 260 mil to 450 mil, and there was different embedment depths into the glacial till, so 2.5 to 3.5 meters into the glacial till. So there was 3 different load tests done, so compression, tension, and lateral, and then there was also some galvanization tests done as well. So I'll touch on that in a minute, but I'll cover the load testing element first. So you can see the loading, the design verification load, and the standard working load for each of the tests here in this table, 1, 3. And then the methodology was the same for each load test. So you can see here a summary of the load test that was done in 1, 2, and the test load cycles that was carried out. So the loading was applied gradually. It was held for a period, and then you can see it was reduced down to 0 of the DVL, and then increased again up to the maximum, which was 100% the DVL plus 200% the SWL, and then it was reduced down again from there, in a similar manner to how it was stepped up. So you can see the top photo here is the compression test being undertaken, and then the bottom photo is the pull-out test or the tensile test. So you can see that there's a load cell attached to the quick hitch, and then there's a deflection device connected up here. Okay, so on the galvanization test then, so due to, I suppose, the aggressive nature of peat, there was all of the specification for the pile in terms of corrosion protection was a ZM620 galvanization coating. And there was some concern by the designer that there may be some damage to the coating when the piles were being installed, particularly between the interface between the peat and the glacial till. So there was a number of galvanization tests done on approximately 15 piles across the site. So what that involved was there was thickness gauge tests done on the pile before they were installed. The piles were then installed, and they were removed subsequently, and the thickness gauge test was carried out again. Yet there was no real evidence of any damage to the galvanization from the install and removal, so that was a positive. In terms of the specification for the pile installation, so it was in compliance with the ICE specification for piling and embedded retaining walls. So that hopefully gives you some summary on the pull-out test campaign that was carried out. And then in terms of the pile design, so obviously the results of the pull-out test were used to carry out the pile design, which was carried out in accordance with EC7 by design by testing. So just on, I suppose, I did mention it around the gravel that was located, the pockets of gravel that was located at the back of the substation. So yeah, there was a number of failures in that area. So there was some additional testing done by the EPC contractor to come up with the final design. And I suppose the final design solution was for pile lengths of between 6 and 9 meters, and a 300 mil Sigma section was the final design. So really, that's it for me. Thank you. I'm going to hand over to Martin Naughton now, who's going to go through his element of the presentation. Thank you.
Okay, so just to introduce the project, Conor has been through the technical aspects, but just the planning and environmental aspects of the project, and how we achieved planning permission, how we discharged planning conditions, and indeed how the site is developed on what was formerly Móna sod peat site, So the peat was removed from the site to particular depths, but the production on site had ceased in the late 1980s. So at that stage, the site was beginning to redevelop habitats within itself in particular areas. So whilst predominantly you would think of a site where there was the peat, the initial vegetated layer had been removed and there was no habitats present on site. That wasn't the case on this site, as the site had begun to recolonize in particular areas. There were particular habitats that had adopted to the site and actually formed on site due to the works that was carried out previously. So keeping that all in mind, there was two applications put in place to Kildare County Council and on Board Penala. So further information was sought as regards the habitats on site, regarding wetland habitats, regarding archaeological, ecological constraints. So bringing all those into mind, there was a comprehensive EIR put together. Within the EIR, there's schedule mitigation measures, and there's 101 particular measures that have to be adhered to ensure that we're in compliance with planning permission. And we also employ a ecological clerk of works full-time on site, and indeed an archaeological watch and brief for the particular areas on site. Regarding the intricacies of the site and what differentiates this site from others is a particular Lepidaria habitats, and in particular the small skipper butterfly, the habitat which is on site, which is a suitable area for the small skipper, and indeed the wetland habitats. So in showing the following picture, you will see the layout of the site. As Conor highlighted, we have a southern array and a northern array. The central column within the site is where the wetland habitats was beginning to establish itself. So we microsited the site, designed it as best as possible to ensure, firstly, we were working in what was the cutaway peatland site. So this is where the production had previously taken place. I've seen one or two of the questions relating to that in the question section. So in doing so, we've ensured that we're not dealing with any virgin peat. We're only working on what was previously cut away. We are out with the wetland habitats and areas which are suitable for further development as wetland habitats, which is also part of our planning condition and part of our EIAR, where we will further develop the site with a rehabilitation plan, indeed before we get to the stage of a decommissioning plan. So presently, the construction is ongoing. At the same time, we will be developing our rehabilitation plan. And then finally, the third phase will be the decommissioning phase, where the site will be returned to a wetland habitat and further developments of other habitats on site. But one of the particular areas and one of the critical areas unique to the site was, just as the access track is highlighted here, in the green section, this particular area is where the Lepidaria were particularly prevalent and ideal conditions for the small skipper habitats. So in order to preserve those areas, we had to work closely with Butterfly Conservation Ireland, develop a plan whereby these particular areas would be left intact and we would be able to work out with the areas. So there was substantial amount of surveys completed and the optimum area was chosen, and we microsited the roads to suit, so as we could construct the project in line with keeping the habitat in its pristine condition. On the right then is just the number of archaeological monuments that are out with the site. There is only one within the boundary of our site, but again, as you can see in the top left here, we microsited the site to suit that we aren't working next to that monument, and we have given it its buffer and all that aspects are dealt with. We kept a archaeologist on site for all excavations. So predominantly our excavations were relating to the substation platform excavation for cable and entrenching, and also for any particular areas, predominantly of the 14K, the majority of it is floating road access tracks. However, next to transformer centres, of which we have 12, you would obviously have to found those particular areas as there was craneage works to be done to lift the trafo into place. So for all those particular areas, and indeed all the works throughout, the archaeologist watch and brief has been on site, developed plans and adhered to the archaeological license. So our program, we commenced in Q3 2022, where our enabling works package commenced. Developed on then to our EBOP, our EPC, our grid energization, and presently we're on track to meet our COD. The works have progressed quite well. It's a particularly quick process in building the solar farm if the conditions are right. It's amazing how quickly it can actually establish and come together. So I just highlight the different packages that were key and fundamental to allowing us to be as efficient as we could in the program. And that was taking into account as much works as you could in the enabling works contract. It wasn't just a package that was there to ensure we had commenced on site, but we put quite a bit of thought into it because in order to facilitate the project and obviously give us optimum commissioning phase whereby we would have sunlight to commission each stage and each transformer center, we had to particularly plan this in timelines. So the initial stage, we had 3K of access track, as I say, floating roads, again, built off ensuring that there was the least disturbance possible, built off existing roads that was there. So particularly easy access tracks to develop. Simply the existing road was in place, lay down your combi grid, having already achieved your CBRs through shear veins or trial pits, etc., and then import stone. The 110 substation platform and associated peat repository area. So just in the top right picture, you can see here the layout of the substation platform, and right next to it we had a peat repository area. So that again would have been a cutaway peat, was a level area which there was all our peat surveys conducted and ensured that the design risk assessment had accounted for this being the optimum area for depositing the peat in place. So that was completed, and indeed the construction compound, again, we wanted the least impact possible there. So of the construction compound, you can see here the area shaded in grey is the only area that was founded, where that the remainder of the compound was floated. A particular aspect that was added to the enabling works contract was our site clearance. The site clearance was being cognizant of when we would need to be working at our optimum would be the late spring to early summertime. So to have removed the vegetation to ensure that there was no nesting birds. Again, all this having been accounted previously that the site was designed where there was no particular areas of nesting birds, but in the event that they may utilize a particular area, we removed the vegetation. We removed the vegetation with a self-propelled mulching unit. So basically, whilst you remove the vegetation and you had a clean level working platform for the operatives to work on, and in particular these projects are more so dependent on personnel carrying out manual handling and access and egress, working through the areas, walking through the areas, and taking that in mind, we needed to leave as nice as and safe of a working platform as is possible. So in clearing off the vegetation, we did so. However, in using a mulcher and a self-propelled unit, we did so with the least impact possible on the ground. But at the same time, the seed bank was retained. So as once we had our infrastructure in place and the next growing season come, the vegetation could then reinstate to its original condition. So that was the process. And in taking that in mind, we had tree felling license from the Department of Agriculture. So we felled where necessary. And again, anything that had established on site was just natural rehabilitation. These weren't trees that were planted, it was just natural rehabilitation since the works had ceased in the 1980s. We then moved on to, once the site was cleared, as I say, we utilized as many existing roads as is possible, upgraded those, utilizing the combi grid 60/40, CBR test done in advance of the required areas of where the combi grid was utilized. And if floating roads weren't applicable, that were only in areas where the 12 transformer centers were to be located. So where you would have your craneage and your outriggers, etc. We had those areas founded. For the substation platform itself, as Connor discussed, there was particular different contents beneath the peat. So you had the sandy silt layer going down to your cobble and better gravel material. That was ideal for our substation platform, and again was encompassed in the design in that we had very little peat to remove there. The peat that we did have to remove, we were down on good ground conditions to found the particular substation platform. But in turn, that brought some issues of support for the piles, as Connor discussed earlier. So anywhere there was better gravel material, in turn, detailed that we required longer piles. But just an overview again to perspective of the site clearance and planning ahead to ensure that you would have the optimum working platform in place for the right time of the year. Those works encompassed all things environmental, encompassed all ecological, and just, yeah, bound into what is the project program. And with that, the BOP contract. So you're prescribed your optimum design essentially with air grid. You discuss what is required for the particular project. In this particular instance is a 110 kV substation. We had the connection quite nearest the dairy line to Maynooth line. So there was only a 0.6 of a looped in grid connection there. You can see in the bottom right picture. So bringing that in mind, when we're working through COVID times and we're working through war in Ukraine, etc. At the particular time, we were looking to get the project going. Lead times and everything had doubled and tripled in certain cases. But thankfully, we were working with a contractor with particularly good contacts and indeed very much so leading in their particular discipline. And 15 months was the lead time for the trafo. And we achieved our grid and energization in August 24. Back then to the access tracks. So with the substation works concurrently ongoing, the EPC contract works were to commence. There's only so much you can do in an enabling works package. As it's an EPC design, you want to ensure that the optimum design is in place and you novate the design to the EPC contractor, but there are tweaks and lead designs that'll change, etc., because it's so dynamic for the particular aspects regarding transformer centers and such works to tie in really. But we had 11k of access tracks in the EPC contract, 12 transformer centers, which are essentially little hard stands, and then you build a bundit area for the trafo to sit down on. The trafos arrived in containerized units, self-contained units, and then you have the bundit area. And obviously that area was founded in order to lift those into place. The Mulgeet box culvert and our drainage works were also particular planning items that we had to adhere to. So in order to ensure that there was no adverse effect downstream of us, we had to install a flow restrictor. So taking into account all the drainage designs, all the preemptive works as regards the flow rates for the water exiting the site, we needed to ensure that when you have removed the vegetation, you removed what is there previous, you've put the panels in place. Obviously the water and the rainwater as it hits the panels was going to be leaving site at an accelerated rate. So we needed to take this into account. We needed to provide attenuation and flow restrictor. So in its simplest form, it was essentially a culvert whereby X water could be discharged off the site at any given site, taking into account all the drainage designs, all the drainage philosophies that was accompanied, all the risk assessments done initially. And this is the process in which we retain water on site. We have the area to do so. The water will have no adverse effect on the site itself, what with the panels being 0.5 off the ground and 0.8 in certain instances. The wet um, the wet vegetated layer again is no adverse effect. So different to other particular sites, be it wind farms, etc., you had the capacity to retain the water on site for the mitigation measure of the water having gained velocity coming off the panels in an accelerated manner off site. The piles, so there was over 60,000 piles installed. As Connor has highlighted, they were a Sigma pile. So essentially, in its simplest form, it's the equivalent of a purlin that you would see on many of the sheds, etc., but in the form of a Sigma shape. The installation of those piles is something that is not widely, well, hadn't been done previously on peatlands, but in its native form on any solar farm, be it of the more established solar farms, in particular for Votalia, who are a French-Portuguese contractor who had carried out EPC contracts throughout the world on large-scale projects. They hadn't carried it out in peatlands previously. And indeed, this was one of the main items which was predominantly overlooked by contractors, in that for them, the installation of piles is a very simple process. Many rigs would install the piles and you would achieve high production rates, and in turn, the upper structure and panel installation was the main area of concern. But in our instance, obviously, working on peatlands and working up to 3 meters of peat, you had to account for the initial process, because if you had disturbed the ground significantly with the excavators while installing the piles, the ground would not have had adequate time to recover to allow the footfall, access and egress for the workers to install the upper structures and indeed the panels, because again, relative to the processes on wind farms, etc., where it's craneage and the footfall wouldn't be that relative to the works that we carry out here, because it has to be manual handling to install the upper structures and indeed the panels. We needed to protect that particular layer, vegetated layer. We needed to protect it in its best condition to allow the works to proceed in a safe manner. And that was our key focus. So Willsbros were appointed as Vitalia's key contractor, having worked previously and worked very well for us on the enabling works process. It was good to see a local contractor bringing forth their innovations and plant and equipment, and really ensuring that Votalia could conduct the works in its localized manner, which it had to, because it was very much so foreign to them working on peatlands. It was very much so a standardized process where mini rigs were set to work to install the piles, a series of mini rigs, and the disturbance of the ground thereafter, it was easily recoverable, it was easy to fix, and then the footfall of the operatives that come into the program sequence, and you would just install the upper structures and the panels. But here we had to protect the ground as best as possible. The utilization of the low ground pressure excavators with Movex hammers was carried out, and was carried out very well. So when you see in the bottom left picture, that was the ideal scenario, to leave as little of disturbance as possible. And also the process and the installation of the piles, it wasn't just a singular line of piles that was installed and the excavator was tracking in between all their works areas. There was a defined route where the excavator would install the piles, and in so preserve the area between the piles, whereby the operatives would then work, and they would install the upper structure, and in doing so, have the best working platform that they could. Then Votalia brought on board their mech and elect contractors, and S&G Solar was the particular contractor that they had chose, as they've worked with them on numerous projects. And again, it was quite a cultural shock for them coming over and seeing the ground conditions that was there, but they adapted, and they adapted very well. And you had all-terrain vehicles utilized, again, the least impact on the ground, and it left it as easy as possible for them to string out the upper structures and indeed the piles. So the dynamic aspects of the project, the adaptation to what was in front of us, was very well carried out, very well coordinated, and very impressive for what was first time working on peatland by Votalia. In terms of the logistics of the project, again, it's one you'd overlook with a wind farm, for example, whereby there's a defined number of deliveries to site each night. With this, you had to initially bring all the piles to site, as I say, 62,000 piles. There then was the 165,300 panels, and you have to do that within a condensed timeline to ensure that you have sufficient quantum of them on site to begin the process, and indeed adhere again back to the planning conditions and the traffic management plan that was as part of the planning conditions. So with that, we couldn't exceed 164 deliveries per day, which seems a lot, but if we hadn't broke the project down into an enabling works process, where we imported the largest quantum of stone to site to build the substation platform, to build the trafo centers, to build the constructors compound, the substation, etc. If we hadn't accounted for that, and you were looking to bring the pile deliveries to site, we would have exceeded that number of deliveries. And in scheduling the deliveries from China, as was Vatalia's right to choose where they brought their particular deliveries from, they had Chinese supplier and Powerway, who supplied both the piles and the upper structure. Again, the beauty of an EPC contract was in that the design was synergies between the upper structure and the pile cannot be discounted or cannot be overlooked. If building a solar farm, the interface and the tie-in between both of those upper structure and the pile has to be on point for the tolerance of which we're dealing with here. And that particular aspect was accounted for with the EPC contractor. So that worked well. And again, as I say, limiting the passes on the ground condition. But this picture here does highlight ground conditions that we had to deal with. But why I like this particular picture when describing the work process, and indeed the program, is in the top right, you can see the contractor installing the piles. In the north of the southern array as such, you can see where they're installing the PV panels. So in order to do that, there's multi workforces working on the site at any given time, no more than on any construction site. But more so this, it's repetition, it's defined. Team A are installing the piles, Team B are coming along, stringing out the upper structure, Team C are assembling the upper structure, Team D is installing the panels, etc. And then your electrical and your commissioning works thereafter, as well as the cabling, etc. But it is a very factory-like system. It is particularly sensitive to any change. So you have to have the components available on site. You have to have the conditions right to work to the optimum as we chase the sunlight, obviously, to try and get the project energized in time, and energized before mid-November is the key. We're on track to do that. The site has went well thus far. We've over 250,000 man hours without any incident, or last time incident, and it's worked really well in that regard. But again, the logistics and the programming to this project, it's particularly sensitive. It's something that we learned with wind farms and anything would have worked on previously. but order of magnitude, this is far more sensitive, and it's worked quite well. Again, just going back to earlier, so there was a question there in the comments regarding the site selection and the peat. You can actually see here the cutaway peat. So this particular area is where the peat was processed, and to the left of it is to the west of it is virgin peat, whereby the areas wouldn't have been touched. So in turn, this site was microsited to ensure that we weren't working on that particular area. And just finally, there is the peat deposition area, and you can see that is beginning to rehab there and get green in color, having kept the US sand, the silts, separate from the top layer of vegetation and re-laid the top layer of vegetation for the optimum restoration of it. So with that, I'll hand you over to my colleague, Shane.
Thanks, Martin, and thanks, Connor, before. So look, I'll just go through, I suppose, where we are now. Maybe it's probably the best way to put this, around commissioning and testing. And I'll just talk a bit about some of the equipment on site, what we're using from a sort of a technical point of view. I suppose firstly here, the bottom two drone photos show the suppose where we're at the minute with the Martin had a picture of the southern ray there in the last slide. So on the left hand side, that was taken about probably 3 weeks ago. So it's a little bit different now. All our solar panels are installed on the southern array. Substation is in the center of the photo on the right hand side, completed. On the right hand side, and that's our northern array. There is a small section left to install a few panels in the bottom right corner there, but that'll be hopefully bombed out in the next couple of weeks. Suppose on our commissioning phase, Martin did say we energized the substation back in August, and with that we powered on our first set of solar panels during September. So the southern array came online first. So since then we've progressed in a sort of a timely manner through commissioning and energization, and as we stand, we have about nearly 75% of the farm energized at the moment. As part of that process, then we're conducting an ongoing series of dispatch testing with EirGrid and Voltalia. So at each step in the dispatch test process, we increase the export potential of the farm by about 15 megawatts. So we 4 tests complete. So we're up around the 60 megawatt mark now. With the nice sunny weather in Ireland at the minute, we're not achieving anywhere near that. But when the sun comes out, it's amazing how quick the farm will run up in the energy stakes. But as Connor alluded to earlier, it is optimized for summer production. So during the winter time, we have that challenge of trying to get production while doing the tests. We do need energy to carry out the dispatch test. So hopefully we'll get a bit of sunshine for the next couple of weeks as we look to get the plant fully online. So that should happen, as Martin said, later on this month, hopefully, all going well. Might flick on there, Martin, if you don't mind. So just a bit on some of the further aspects of commissioning and I suppose more about the equipment on site. So we have string inverters on site. So we have 248 individual inverters. That's a little picture of them there on the right hand side. So you can see them mounted to the back of the table underneath the solar panels with the warning signs on. And the cables going in underneath there, the MPPTs, so they come from each of the strings, each solar string or each panel string on the tables. Their inverters are manufactured by Huawei. Input voltage on the DC side, so the panels are connected in series, and there's 1500 volts going into the inverter on the DC side, and it outputs it then in a 3-phase 800 volts 3-phase AC. So each inverter outputs that sort of amount. So they're all connected in parallel to the transformer centers through LV cables. So there's a question there about ducting and items like that. So the LV cables themselves, we direct bury the LV cable. The MV cables between transformers is ducted. each inverter, there's about between 18 and 22 inverters per transformer. So it's sort of slightly different depending on the design of the individual areas. The communication is quite interesting now from my point of view. It's not, the inverters aren't connected with a fiber cable. So they actually communicate to the transformer center through M-bus, which essentially uses the low voltage cable to communicate. It's pretty interesting. It took me a while to get around it now. I am a civil engineer, so bear with me on that one. There's around 23 PV strings connected each inverter. So about 690 PV panels per inverter. Now, if you multiply that by the 248, you're not going to get 165,300. Some are size less, so it just depends on the layout of the particular inverter. All the PV panels come from Trina. There is a question there I've seen in the chat box about supplying the panels. So the EPC contractor was responsible for procuring and supplying the panels and also installing. So the client didn't get involved in procuring panels on this project. There's 3 panel types. So from 650, 655, 660 watt. So they're a very large, pretty large panel compared to your domestic panel, probably 200 watts bigger, very physically large. They're about 2.4 meters high, 1.4 wide. So they're big lumps, about 35 kilos each. There's 165,300 of them. So you can imagine there's a huge quantity on site to be handled and installed individually. So a lot of manual labor went into installation. So a lot of lifting, a lot of connecting, a lot of bolting. Just some of the commissioning tests that the guys do once installed. That kit there on the right hand side is what tests the PV string. So your normal voltage, current, continuity, and then they do a little output test on the panels just prior to connecting the PV string. So they do need a bit of sunlight to actually test the panels before we connect and generate. Then also prior to energization, the commissioners will update the software on the inverter. So they can do that centrally. They don't need to go around to each inverter. They can do that centrally at the transformer center, and it'll send down the software updates to the inverters, and they'll update again, and also check the SCADA communication back to the substation. So every element is connected with SCADA to a centralized power park controller, so we can control the entire farm sitting at our desk, and that'll hopefully be the future. At the moment, there's a little bit of over and back because we're only commissioning, but when we're finished, we'll be able to sit down and monitor things. All right, Martin, you can move on there to the last slide. So I'll just speak a little bit about some of the community environmental benefits to the site and the works we've carried out. So as Connor said earlier, enough power to power about 25,000 homes when it's up and running. As part of RES, the project has to put about €2 per megawatt hour generated into a community benefit fund every year. So there'll be probably about €200,000 each year going to projects in the locality. So like the local clubs, local GA clubs, youth clubs can apply for that funding each and every year, and there'll be a process then to give out that money and rate the projects that they have. So I suppose this is it's a widespread thing with Móna and ESB's other projects, that each of the RES and some of the refit projects have community benefit funds. So it's a big bonus for the community. As part of the planning and as part of the works, we constructed a 6.5 kilometer amenity walkway. So that drone shot on the left shows some of the walkway. It kind of goes away from some of it runs down alongside or adjacent to the panels. So this end of it actually takes in some of the revegetated area on the existing peatland. So it does a little bit of a loop and you can walk in and walk out. So that'll be open to the public. It's probably going to be probably mid next year before it gets officially open. But members of the public can come in and walk and park their car and enjoy the scenery in North Kildare. And then as part of the planning and finally rehabilitation of the site, there is a habitat enhancement plan that has been developed, and that work will be carried out in in conjunction with Board of Móna has their own internal rehabilitation. Well, we call it the PCAS side of the business. So they come in and rehabilitate the peatlands. So the hope is that Timahoe will undergo a level of rehabilitation in the next, hopefully in the next 12 to 18 months, in areas that'll be earmarked for that, and that'll preserve the butterfly habitat as well that Martin went through earlier, which is on site. So yeah, look, that's the end of the presentation. Thanks everybody for listening.